week, we are moving on in Chapter 7. And we're continuing with the theme of root radicals and root functions. We're going to be able to multiply radical expressions, so we're picking up where we left off last week with combining those like terms that are considered to be radicals. We're going to work on rationalizing denominators with one radical term, and then work on rationalizing binomials with a radical. And then last, we're going to write radical quotients in their lowest terms. So we're kind of taking that arithmetic we did much earlier in that elementary algebra class, and we're applying it all to radicals. So here I have a distributive property, right? There's something in front of the parentheses where I've got an operation that is occurring within the parentheses. So when we distribute something, that means we give one to everybody in the room or in the group. So in this case, in A, I'm going to distribute the square root of 11 to 5 and to the square root of 2. I'm going to do this through multiplication. So I multiply each term by the square root of 11. Now, I can't combine the square root of 11 and the square root and 5. It's not going to make something simpler, so the convention is to write the 5 in front of the root. However, the square root of 11 times the square root of 2 can be further simplified into 11 times 2. So I don't do that in the first part of the problem because the 5 is not under a radical. Then I look at that and I say, okay, is there anything I can do to simplify? Is 11 or 22 divisible by a perfect square? And they're not, so we're done. In part B, we're distributing a number into a radical expression, which means it cannot be simplified any further. To be able to simplify something, if I did the square root of 49 times the square root of 54, that would be making things more difficult. So we just write the number in front and there's nothing further we can do. Then we look at it and we say, okay, this is as far as I can go with the distribution. Is it divisible by a perfect square? Well, 54 is divisible by 9 and 24 is divisible by 4. So then I have 7 times the square root of 9 times the square root of 6. 7 times the square root of 4 times the square root of 6. So I'm going to take that square root of 9, which is 3, and I'm going to multiply it by 7. That's where the 21 comes from. I'm going to take the square root of 4, which is 2, and multiply that by 7, and that's where we get 14. Now, these radicals are like terms because I have the square root of 6 and the square root of 6, so I can actually go ahead and complete that subtraction of 21 minus 14, which is 7. So notice these problems, they're simple concepts, but they're really going to pull on what you learned last week. Now we can FOIL with radicals. I know, everyone just took a deep breath. So we do first, outer, inner, last. This is a review from what you learned in the elementary algebra class. So the first would be 2 times 1, which is 2. The outer would be the square root of 5 times 2. And we can't combine that because they're different terms. I have 2 in the front. Plus the square root of 3 times 1, which is just the square root of 3, plus the square root of 15. Look at this. That's a doozy, right? That is all I can do. I have no like terms. Do y'all see that as the square root of 5 and the square root of 3? I can't combine those in any way, and they're not divisible by a perfect square. The same happens with 15. While 15 is a multiple of 3 and 5, I have to use perfect squares to reduce the radical. So I can't do anything here. So sometimes in the lab, you might be getting just really long expressions, and that's okay. In part B, I'm going to do the FOIL process again. So 4 times 4 is 16. 4 times the square root of 5, negative, it would be minus 4 square root of 5, plus 4 square root of 5, minus 5. Where does the 5 come from? The square root of 5 times the square root of 5 is the square root of 25, which is just 5. Now notice those middle terms. I have minus 4 square root of 5 plus 4 square root of 5. Those are going to cancel out. And I'm going to have 16 minus 5, and I get 11. So we can get really complicated expressions or really simple expressions. And then the last one, this is not the square root of 13 squared minus 2 squared. That is the most common mistake that I see when students are working with this. You actually have to write that out as the square root of 13 minus 2 times the square root of 13 minus 2. So you can use FOIL. So this is my FOIL. And looking at this, I have not quite the same thing we had in B. We have minus 2, minus 2. They're like terms. So if I have a negative 2 minus 2, that would be negative 4. And then I have 13 plus 4. I can combine those like terms into 17. So now we've kind of visited every scenario that's possible. We could just get one term. We could get 4. Now we have the possibility to get 2. 13 can't reduce any further, so you're done in part C. So we're going to look at another FOIL. First, outer, inner, last, and then you look at what you get. I have the cube root of 7 squared here, but then I have just the cube root of 7, so I can actually do something with these middle two terms. I can do minus 4 plus 4. Those terms are going to cancel out. And then I go ahead and type in 7 squared is 49. Can the cube root of 49 be broken down? No, there's no perfect cube that's divisible. We learned that in the last section. And then the 16 remains as is. Now E, look at this. The only difference is the sign in the middle. So if those of you who remember from elementary algebra, you are a difference, sum and difference of squares, that's what this actually is. However, you can also take a look at it and be able to do first, outer, inner, last. So if we're using the difference of squares formula, that is where, because it's a plus and a minus, you square the first and you square the last. But you could also FOIL this out and get the square root of r times the square root of r, which is where that comes from. You could do the square root of r times the square root of s, which would be square root of rs. Same thing here, but one's going to be a minus and one's going to be a plus, and that's where the cancellation is going to happen. And then I have square root of s times square root of s. So that's where this comes from. Or you could apply the sum and difference of squares formula. When I square a square root, it goes away, and I just get r minus s. Now we're going to rationalize denominators. There's a chance you've already seen rationalizing denominators, but you may or may not quite remember it, so I'd like to go over it. A common way of standardizing the form of a radical expression, so something with a radical, is a denominator that cannot have a radical. This is very common in math. We don't like having that, just like we don't like having negative exponents. So we do this process called rationalizing the denominator. And this is done by multiplying the top and the bottom by the value in the denominator. If I multiply the top and the bottom by the same thing, like 2 over 2, 3 over 3, it's called a form of 1 because 3 divided by 3 is really just 1. So I'm not unbalancing my equation because technically I'm multiplying by 1. So if I want to rationalize the denominator in A, I need to get rid of the square root of 11. So I'm going to multiply this by the square root of 11 over the square root of 11. And it's considered a form of 1 because that would reduce to 1. Now, I just have 5 times square root of 11. There's nothing I can do there to make it simpler. The square root of 11 times the square root of 11 is considered the square root of 11 squared, which is just 11. In the bottom, in B, I only want to rationalize the denominator. I don't want to look at that square root of 6. So when I create that rationalizing statement, I'm going to leave the 6 alone. And I'm going to multiply by the square root of 5 over the square root of 5. Square root of 6 times the square root of 5 would be the square root of 30. And then here, that root is going to cancel out because you're going to have the square root of 25, which is 5. So rationalizing the denominator in the lab, it will not take your answer as correct if you do not rationalize the denominator. So while the question may not explicitly state to rationalize the denominator, all final answers have to be rationalized. And then at this point, I have a 5 in the top and a 5 in the bottom, and I can go ahead and cancel those out. Here, I have a square root of 18. It doesn't matter that the top has a negative in it. That changes nothing about the process. Now, what do they do here? They decided to simplify the radical before they rationalized it. If you chose to rationalize it first, is it wrong? No. It just may take an extra step or two. So you could go ahead and multiply by the square root of 18 over the square root of 18. That would be fine. But Because the square root of 18 does reduce and it's divisible by a perfect square, the best practice is to go ahead and cancel and reduce it before we rationalize. So here, I need to rationalize by multiplying by square root of 2 over the square root of 2. They're going to cancel in denominators. So I'm going to have 3 times 2, which is 6. Then I'm going to have that negative 8 times the square root of 2. Again, there's 2 different pathways to getting to the answer. Either pathway gets you there. It's just that it's a best practice to go ahead and reduce a root. And then what happened in this final step, I can reduce 8 over 6. I can divide both of those by 2, and I get 4 over 3. Again, the lab is going to expect you to fully reduce all fractions and to rationalize all denominators. All right, so here we go with one we kind of saw last week. This is the square root of 8 divided by the square root of 45. So I can distribute that radical to each term. Now, I'm going to have to rationalize the denominator. So first, let's just look at 45. Is it divisible by anything that's a perfect square? It's divisible by 9. Then I look at 8 and I say, 8 is divisible by 4. Let me go ahead and simplify these into 2 over 3. The 2 comes from the square root of 4. The 3 comes from the square root of 9. Now I can rationalize by multiplying by the square root of 5 over the square root of 5. I'm going to combine those radicals and get 10 at the top. And at the bottom, the square roots are going to cancel, so I'm going to have 3 times 5, which is 15. 2 and 15 are not divisible by any value. It would be the same for the top and the bottom. So I can't reduce that any further. And then the square root of 10 is not divisible by a perfect square, so the radical is fully reduced, and I can go ahead and enter my answer in the lab. All right, now let's look at this one. This one is a little different, right? Because I have a variable in the radical. So I go ahead and distribute the radical. That's the first step we're going to do. Now I'm going to think, can I simplify y to the 7th in a radical form? Well, I can make it y squared times y squared times y squared times y. And all of those y squareds will be able to simplify. The same is true with k. I could write k as k squared times k squared times k squared, just like we did in the previous sections. I can break 200 up into the square root of 100 times 2. Now, why did I take the time to say those products out loud? Because some students don't always understand how to simplify k to the 6th. With the square root, it's just division by 2 because it's a square root. So I would get 10. 6 divided by 2 is 3, and that 2 is still underneath the root because it's not a perfect square. 6 divided by 2 is 3, and then I still have the square root of y hanging out. This is not a final answer because I still have to rationalize my denominator. And I have y to the 3rd times, remember the square root of y and the square root of y is just y, not y squared, y. 3 plus 1 is 4. And then another example would be a cube root here. It's good to work with cube roots. We don't see those a whole lot. The cube root of 15 divided the cube root of 32. Now, when I look at 32, I've done so many problems over the time that I think, that might be something I can reduce. 15, not really a lot I can do there. 32 is divisible by 8. So remember your perfect cubes would be 8, 27, and so on. You're going to go through there. So I can simplify the cube root of 8 to 2, and then I can rationalize that denominator. And when we're rationalizing the denominator, it's a little bit different when I have a cube root. I'm going to have to multiply by the cube root of 2 and the cube root of 2 on the top because that gives me the cube root of 8. So when you rationalize a cube root, you do not multiply the top and the bottom by the cube root in the denominator. You have to get a perfect cube. So 4 times 2 is 8. 8 is a perfect cube, and that's what gets rid of the radical. So that's why cube roots are going to be different, and there is a question in the lab that's the style. So cube root rationalizing is not the same as square root because a cube root times a cube root does not cancel. So then I get the cube root of 8, which is 2. So I have 2 times 2, which is going to be 4, and the cube root of 30. Is there anything I can reduce the cube root of 30 by? It's not divisible by 8. It's not divisible by 27, so it's pretty much in final form. A fourth root is going to be the same thing that we saw in a cube root. It's not necessarily going to be as simple as just rationalizing the denominator. But I have this w squared. So what do I do to w squared to get it to cancel? Well, if I had w to the fourth, it would cancel. So the reason I'm multiplying by w squared over w squared, the fourth root of it, is because when I multiply w squared times w squared, that would be w to the fourth. This would be different if it was just a w in the denominator. So it's not that I'm really multiplying by the denominator. It's that the fourth root of w to the fourth cancels out that root. And that's as far as I can take it. So now I want to look at rationalizing denominators with binomials, with radicals. So we're going to use what we call a conjugate. So look at the denominator, 1 plus square root of 2. In a conjugate, we're not flipping anything. That's a really common practice is we want to flip something. We're not flipping it. We're only changing the sign of the middle. We don't change the sign of the front. We just change the sign in the middle, and that will create a difference of squares. All right, so let's look at how this works. I'm going to multiply by the conjugate because I have two terms in the denominator. One of them has a radical. The conjugate would be 2 plus the square root of 3. Now I'm going to FOIL my denominator. When I FOIL the denominator, I get 2 times 2, which is 4. But you see how they skip this step? Negative 3 square root of 2 times 2 would be minus 2 square root of 3. Then I have the outer, which would be 2 times the square root of 3, but it's positive. So that middle term cancels, and that's why we got 4 minus 3. So go ahead and go back to the FOIL section. Take a look at how that sum and difference of squares that I pointed out works. That's why we looked at that here. Square root of 3 times square root of 3 is 3. So I just simplify this into 1. And then remember, when something's written over 1, we don't have to write it over 1. And then I can distribute the 4. Now, is the lab going to accept the 4 in the front? No. You would need to distribute it to have a final answer that's fully simplified. That's a common question we get. So same thing here. I'm going to multiply by the conjugate. So I get square root of 2 times square root of 2, which is just 2. Square root of 13 times square root of 13, which is just 13, using that sum and difference of roots formula. Now I'm going to have to distribute the 7 and simplify 2 minus 13. And if you notice the difference in A and B, the negative is in front in the numerator, or it's in the denominator. The lab will take either way. It does not have to be in the top, it doesn't have to be in the bottom. Either one will work. So this is not saying these are both answers. It's saying depending on where you put the negative, you could get either answer. Because I have two radicals, I could distribute the 7 and the lab would take that as a correct answer, but it will also take this factored form as a correct answer because when I distribute that 7, it doesn't actually combine with the root. So slightly more complicated FOIL here. You are going to FOIL the top and FOIL the bottom. But in the bottom, that middle term will cancel out. And we're going to be left with 2 minus 7. Ooh, then I look at all these top numbers and I think, is there anything I can do to simplify 6, 21, 10, and 35? Are they divisible by 4, by 25, by 8? Any perfect square or a number that's a multiple of a perfect square? I don't see anything here. So I'm done. And then again, you could write that negative in the top, or you could write it in the bottom. Here we have a similar situation. We're going to multiply by the conjugate. We're going to FOIL the bottom. We do not have to FOIL the top. I get k minus z. K minus z, it is what it is. I can't take it any further. I can't subtract those numbers. That's it. You could distribute the 2. The lab would still take that as a correct answer, but you don't have to because both terms are radicals. So this is a common place where we have errors within our simplification because I can't combine 24 and 36. They are not like terms because 36 has the square root of 7. However, is every term in there divisible by a common factor? Well, 24 and 36 are both divisible by 12. So what I can do is I can factor that 12 out just to make things a little simpler in a minute. You're going to see why. And then I look at 12 and 16, and they have common factors as well. They have 4 in common. So I could do 12 divided by 4 is 3. 16 divided by 4 is 4. And I could cancel those factors out because they're in both. And I could either enter 3 times the front over 4 or the other way. Now this is what I do. I do this a little bit differently than the book teaches you. I look at 24, 36, and 16. I say, okay, all of these are divisible by 4. 24 divided by 4 is 6. 36 divided by 4 is 9. 16 divided by 4 is 4. So I skip straight from this A step to this B step, and you can certainly apply that to your problem solving as well. You do not have to do the middle steps. You can look at it as every value, number value, divisible by the same thing in every term. Then we go to part B. Part B is a little different because I've got this square root of x squared, which first of all, I can do something with that. And second of all, I can reduce the square root of 32 into 16 times 2. So I simplify that and I get here. Again, I'm going to skip any factoring out steps the book shows, and I'm going to say 2, 4, and 6 are all divisible by 2. So I will divide every term by 2. Every term also has an x, so I will divide every term by x. And I'm going to get 2x divided by 2x is 1. 4x divided by 2x is 2. 6x divided by 2x is 3. So you can skip that's factoring out step there. And that's the end of the section. I know it's been a long lecture, but you guys have this.